Hey everybody, welcome back to Linear Algebra Online. So this is going to be our chapter 6 abstract vector space review video. I just want to go over kind of a few key things from the unit, and a lot of the problems in here are actually going to be kind of like proofs and a little bit tougher, I think, because those are historically like the harder problems. And I kind of want to also build up to the point where I can really argue that in a linear transformation, a basis goes to a basis, which is a super handy thing to know. This was actually a problem just from our problem set, and I just kind of wanted to sketch out how I would do this. One of the most important things in this unit is just being able to analyze linear transformations and find the rank or nullity of a certain map or something. So these are 3x3 matrices, and the transformation is A minus AT, like T of A goes to A minus AT. And so we want to find the rank and nullity of that map, right? So the easiest way to do this, I think, is basically to let 0 equal T of A, right? But T of A is A minus AT. So if you think about what that's saying, basically it's saying A equals AT, or A is symmetric, right? And so then that means that anything in the kernel, right, is going to be defined by a symmetric matrix, okay? And for 3x3s, that would take 6 basis vectors, right? Because just to kind of show, so I guess I'll do this. So script B for a symmetric matrix is, you could do this as a basis vector. You could do, all the diagonals really. I'm just going to do that. And then 0, 0, 1. And then you could also start doing these kind of things. We have 0, 1, 1, 0, 0, 0, 0, 0, 0, and so on, the other kind of cases for that symmetric kind of structure, right? The other cases being these two and then these two. And so here there are 6 basis vectors, right? So this implies that the kernel of T has 6 things in it. So the nullity of T is 6, right? And then we know that by the rank theorem, right? We know that the rank of the transformation plus the nullity of the transformation should equal the dimension of the space, and this space has dimension 9 because 1, 2, 3, 4, 5, 6, 7, 8, 9 different spots there. You could kind of take a basis for this, just be 1s in everything there. So it has to equal 9. So then you get this brilliant math equation that says x plus 6 equals 9. So x, if you move the 6 over, is 3. So this implies the rank of this transformation is 3. And just what that means is it sends quite a bit of stuff to 0, right? It sends 6 dimensions worth of this original 9 dimensions to 0 in the map, and only 3 dimensions get sent through and are non-trivial. So that's a very important thing in linear algebra, just being able to analyze those different maps and things like that. All right. So what I want to do now is kind of build up to this important idea where I'm going to argue that basis vectors go to basis vectors in a linear transformation. So to start off with that, I want to talk about this. So if you have this map, T going from V to W, and it's a linear transformation, and you have a basis, V1 through Vn that spans V, then I want to show that t of that basis, which is just like t of each vector, will span the range of t, all right? So the idea here is basically show that like w in like w is in the span of t of b. Basically, something in the range of t that is gets spanned by t of b. And maybe actually the better thing to do is, I'm actually going to be more specific because we don't necessarily know this map is onto, right? So there might be things in W that aren't in here. I'm not necessarily saying it's an onto map. I'm just saying that something in the range of t, right? So t of v is definitely in the range of t, is in the span of t of that basis set in v, all right? So basically I need to show t of v equals like a linear combination of t of the basis right here. So this is, for v in v. Okay, I guess I should probably add that just to be super clear. But, since v is in v, we could say since you have this basis for v, then vector v should equal a linear combination of, v1 and v up through vn, right? And t is linear, right? T is linear. So if I just take like t of both sides, then t of v will equal like t of c1 v1 plus blah 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 plus cn vn. But the linear part gives me that I can pull the scalar out and also do the sum of t of the sum of all these things. So this is basically going to do it for us. And so what that says, right, is that t of v is a linear combination of t of v1, t of v2, t of v3, and so on, which basically just implies that t of v is, in the span of t of b. T of v is a linear combination of all these different T of v1, T of v2 kind of things. That is what we define as T of the basis. So this is nice because it shows that the linear transformation on a basis set for the original space is going to still span the range of the transformation, which is good. And it's a stepping stone towards the ultimate thing I want to show here. All right, so this was a theorem in the last video that I used when showing two things are isomorphic, but I didn't prove, and I actually do want to prove it now. And I also actually will use it in another proof here in a second. So this was the one that said that if your two vector spaces have the same dimension, and you got a linear map that is like 1-to-1, then you get onto for free. Or if it's a linear transformation that's onto, you're going to get 1-to-1 for free. Super, super, super useful, and honestly used so often in proving things are isomorphic. It's a very common theorem to use. So really to do this, we can just use like the rank theorem, and you'll see here. So I'm going to start off. And and show that assuming 1-to-1, I'll get onto. So this is basically the forward direction. Assume t is 1-to-1, and we show t is onto. All right. So if, since I guess I should say t is linear and 1-to-1, we know by another previous theorem that the kernel of t is just the trivial, 0 vector. That was like a thing we proved in a previous video somewhere, very useful to know. So then you can use the rank theorem. By the rank theorem, right, because that just has definition or dimension 1, right? Or dimension 0. So by the rank theorem, I don't know if I can fit it in there. The rank of this transformation would just equal like the dimension of V minus the nullity of that transformation, which would just be like n minus 0, right? And so this implies that the transformation is full rank. So T is full rank and sends all info to W, so T is onto. Basically, everything in W must get hit by something because it's full rank. So then for the reverse direction, go backwards, now we're going to assume T is onto and show T is 1-to-1. Right? And basically it's just rank theorem, but kind of going backwards with it. In this case, you know the rank of T now equals the dimension of W, and both equal n. So the nullity of the transformation, which equals the dimension of like V minus rank of T, would just equal n, right? Minus n, right? And so that equals 0. So the kernel is the trivial 0 vector. Hence, by that other theorem again, T is 1-to-1, right? And it does it. So that's just like a very, very, very handy thing, and it's tied directly to the fact that it's a linear transformation. But if it's linear, you're going to get like 1-to-1 for free from onto, and onto for free from 1-to-1. So when you do those like isomorphism proofs, and you like show that your the map you defined is an isomorphism between like vector space like V and W or whatever, you really just need to show that it's a linear map and then that it's 1-to-1 or onto, and you'll get the other one for free. All right. So another thing I just want to show is that if you have a 1-to-1 linear transformation and you have a linearly independent set here in V, again, V to W, then T of S, which is like T of all those things, is also linearly independent in W. If you kind of think about what it means to be a basis, right? One of the things that we need for a basis is that your set is linearly independent, and that is what we're building to here in this video. So I'm getting close to the point where I can really argue that a basis goes to a basis, which is a super important thing to know in linear algebra. So to do this, basically, I just do the standard thing. I basically given like C1 TV1 plus plus C2 T V K, I guess here, equals 0. We wish to show that C1 up through C, I don't know why I wrote 2 there, sorry. It's supposed to be a K. This one's a K. Need to all equal 0, and hence T of S is linearly independent is the idea, right? Standard proof technique for showing linear independence. Like the combo here, you need to argue why the coefficients are equal to 0, and then if you do that, you'll have that this stuff is linearly independent. All right? So since t is linear, right, if I had this, right, and I should copy it down here. Since it's linear, I can basically write it this way. I could say, you know, that's the same as, so this is since t is linear. It'll be the same thing as t of c1 v1 plus blah, 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 c k v k, right? And all of that has to equal 0, right? Because I'm just taking t of 0, and we know that the 0 vector goes to the 0 vector. So I guess, you know, maybe I could write it just to be clear what I did there. Basically took t of both sides, use the linearity, and so you get 0. And this implies that this vector in here, so c1 v1 plus blah, 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 ck vk, is in the kernel of t, right? And t is 1 to 1. So by that theorem we've used a bunch, right? That means that the kernel of t is trivial. It's just the 0 vector, right? So c1 v1 plus blah, blah, blah has to be equal to that 0 vector, right? And this does it then, right? Because if the set v1 vk is linearly independent, which we know it is, then all the c's are equal to 0, right? And that's going to prove it. So this implies all these c sub i's, let's just say, equal 0, since v1, I'm just going to say, it's defined up here as s. Since s is linearly independent, right? Therefore, the set t of s is linearly independent, right? Because those c's are the exact same c's that I started with up here. So it's kind of a clever little use of it there. But that would prove that if you have a linearly independent set in V, you take t of it, given a one-to-one linear transformation, then your output of t of s here will also be linearly independent, which is going to be very useful for this. This is the hugely important thing I've been trying to build up to. So given the same dimension, then a one-to-one linear transformation will map a basis to a basis, which is super, super nice, okay? This is basically how, in that video where I built up the matrix of the derivative, this is basically how I did that. It's how you can do so many other things in math. You know, I've talked about that like PhD arrow kind of thing. So much of building maps is knowing clever ways to sometimes just defining them, right? And then knowing whether or not your map is nice and actually isomorphic. All right, so if you look at what this is saying, so we have the same dimension. We have a one-to-one linear transformation. And we want to show that this thing will map a basis for V to a basis of W. Super, super handy. And honestly, it really just uses a lot of what I've already shown in this video. So, you know, this last proof, basically it said that, like, if it's a one-to-one linear transformation, which is what we have, right, then T of a linearly independent set is a linearly independent. So let's just say, actually, I guess B is a basis for V. V1, Vn is a basis for V. So by the last theorem, we know that T of B is linearly independent, right? And now we just need to show that T of B basically spans W. And that would do it, right? Because then we would have a linearly independent set that spans the space W, and so T of B would be a basis, okay, for the space. And that utilizes, well, two things, I guess. It utilizes this. So by this theorem, right, T of B will span the range of T, all right? So by another previous theorem, basically we have T of B spans the range of T, but since T is 1-to-1 and linear, right, we know T is also onto, right? You get that for free. So the range of T, right, is W, right, which is what we want. So T of B is a basis. That's a horrible run-on sentence, but I don't care. T of B is a basis for W, right? And this is just like super important because now what we're saying is like given, some important conditions, but we can basically try to figure those out, all right? We know that a basis in V will just get mapped to a basis in W. And so it kind of gives us a nice, easy way to build maps between spaces. Just to kind of show you this. So say we have, R2 to P1 given by this transformation. This is dimension 2. This is also dimension 2. This is also actually a 1-to-1. I'm just going to let you believe that. This is 1-to-1. We could prove it, but it is a 1-to-1 map, right? And just to kind of show you how this sort of feels, if you want to take a basis element from R2, it should go to a basis element for P1. So like T of the standard basis for R2, which is just 1, 0. If you just use this map, it says we're going to go to 1 plus x, right? And then T of E2, which is just T of 0, 1, would go to, what would that be, 0, 0, so just go to x. So therefore, it means that the set x and 1 plus x is a basis for P1. That's kind of how we use this in practice. A lot of times you do have to you have to prove the linear part, you have to show it's 1-to-1. But then if you have that kind of stuff, you can go ahead and get a basis for another space, which is super handy. So this is just another kind of thing I wanted you to see. Kind of ties in a lot of important things from this unit. And that's about it.